March 1942. Quonset Point, Rhode Island. Walter Grosvenor's hands wouldn't stop shaking, not from fear, from exhaustion. The Navy civil engineer had been awake for 51 hours straight, fueled by nothing but black coffee and the crushing weight of failure sitting in his chest like a stone. He stood in a warehouse that smelled of machine oil and wet metal, staring at what should have been his breakthrough. Instead, twisted steel panels lay scattered across the concrete floor, like the wreckage of some failed experiment. Which is exactly what they were. His third prototype in 3 weeks. His third disaster. Outside, a late winter storm hammered the corrugated roof with rain that sounded like artillery fire. The same rain that was supposed to prove his design could handle Pacific typhoons. The same rain now dripping through 17 separate leaks in the prototype, pooling around his boots, mocking every calculation he'd made. Grosvenor pulled the telegram from his pocket for the 100th time. The paper had gone soft from constant handling. The words burned into his memory. Japanese advance unstoppable stop. Need 5,000 shelter units. Pacific Theater by July. Stop conventional construction. Impossible stop approve. Radical solutions. Stop radical solutions. That's what Washington called it when they had no idea what to do and desperately needed someone else to figure it out. The math was simple and terrifying. Today was March 15th. July was less than 4 months away. They needed 5,000 complete shelter units designed, tested, manufactured, and shipped halfway around the world. Units that didn't exist yet. Units that nobody knew how to build. And that was just the first order. The real number haunted his dreams. Field commanders were requesting shelter for 2 million personnel spread across hundreds of islands they hadn't even captured yet. 2 million men who would be sleeping in mud, getting sick, dying from pneumonia and tropical diseases because Grosvenor couldn't figure out how to bend steel properly. He kicked one of the failed panels. It clanged against another piece, the sound echoing through the empty warehouse. Somewhere in the darkness, water dripped steadily through another leak. The British had sent their Quonset Hut blueprints 3 weeks ago. Semicircular steel tunnels they'd been using since World War I. Grosvenor thought adapting them would be straightforward. Just modify the dimensions, adjust for Pacific conditions, and start manufacturing. He'd been catastrophically wrong. The British design required concrete foundations that didn't exist on coral atolls. It used wooden internal frames that would become termite food in tropical climates. Each hut weighed 3 tons disassembled, requiring specialized equipment just to move the pieces. The ventilation system worked fine in Scotland, but would turn these things into steel ovens in Philippine heat. And now his attempt to fix those problems had created 17 new ways for water to pour through the roof. Grosvenor checked his watch. 3:47 a.m. In 5 hours, he had a meeting with Admiral Whitmore, who would ask for a progress report. What was he supposed to say? That they'd burned 3 weeks and had nothing but failure to show for it? The warehouse door opened with a metallic screech. A woman's silhouette appeared, backlit by the security lights outside. "Still here, Grosvenor?" Judith Reardon's voice cut through the sound of rain. Or, "Did you finally accept that you can't solve this alone?" He turned to face the structural engineer he'd been told to expect. She stood in the doorway holding blueprints under one arm and what looked like a thermos of coffee in the other. "I'm not sure anyone can solve this," Grosvenor admitted. Reardon walked into the warehouse, her boots splashing through puddles, and surveyed the wreckage of twisted metal around them. "Then it's a good thing I don't work alone, either. Marcus Chen is waiting in your office. We start in 20 minutes, and we're not stopping until we have something that actually works." She handed him the thermos. drink. You look like death. And we've got 57 days left. 2 months earlier. December 1941 through February 1942. The reports started arriving at the War Department in Washington 3 days after Pearl Harbor burned. At first, they came in scattered bursts, fragments of information from commanders too busy fighting to write detailed assessments. But by January, the messages formed a pattern that terrified everyone who read them. The American military was losing men to an enemy that never fired a shot. Lieutenant Colonel Harrison Webb sorted through the morning dispatches in his cramped Pentagon office, and each one made his stomach tighter. From the Philippines, entire platoon hospitalized, respiratory infections, tents collapsed during storm, men sleeping in standing water. From Wake Island, supply depot flooded, 3 weeks' ammunition ruined, canvas shelters disintegrated, request immediate replacement. From Guadalcanal advance reconnaissance, fungus growth destroying equipment within 48 hours, salt air corroding metal fasteners, existing shelter designs unsurvivable in these conditions. Webb had been a logistics officer for 15 years. He understood supply chains, construction timelines, and resource allocation. What he was reading shouldn't be possible. The United States had more manufacturing capacity than any nation on Earth. They could build tanks, aircraft carriers, and bombers fast enough to supply 2 theaters of war simultaneously. But they couldn't figure out how to keep rain off soldiers' heads. The problem wasn't complexity. It was impossibility. Traditional wooden barracks required skilled carpenters, and every carpenter who knew how to swing a hammer was already building ships or working in aircraft factories. Each barracks took 6 weeks to construct and cost $8,000. The Navy had calculated they would need 18 months just to build conventional housing for the forces they needed to deploy immediately. 18 months. The Japanese would own the entire Pacific by then. Standard Army tents cost $12 and could be erected in an hour. Perfect solution, except they lasted exactly 1 month in jungle conditions before monsoons tore them apart. Soldiers were writing letters home, describing nights when they woke up with their boots full of water, uniforms covered in mold that grew overnight, and tent poles that snapped during storms, sending men scrambling through mud at 3 in the morning. The medical reports were worse. Respiratory infections were hospitalizing more men than enemy action in some sectors. Pneumonia, fungal infections, diseases caused by sleeping in wet conditions week after week. The tropical environment was doing what the Japanese military couldn't, breaking down American forces before they ever saw combat. Webb pulled out the projection his team had calculated. The numbers made him feel sick. To support operations across the Pacific, they needed shelter for 2 million personnel. Not eventually. Now. Across hundreds of islands, many of which were nothing but coral and sand, with no infrastructure, no power, no construction materials. Islands where temperatures averaged 95 degrees with 90% humidity. Where typhoons appeared with winds exceeding 140 miles per hour. Where salt air corroded metal. Termites ate wood, and fungus grew on anything that held moisture. Build wooden barracks? 6 weeks per building, requiring skilled labor that didn't exist and lumber that couldn't be shipped. Use canvas tents? They'd need to replace them monthly, creating a logistics nightmare that would consume shipping capacity needed for ammunition and food. There had to be a third option, something that could be manufactured quickly, shipped efficiently, assembled by exhausted men who'd never held construction tools, and survived conditions that destroyed permanent buildings. Webb gathered the reports and walked down the hall to Brigadier General Hauser's office. The general looked up from his own stack of bad news. "How bad?" Hauser asked. "We're going to lose the Pacific because we can't keep our soldiers dry," Webb said. "And I have no idea how to fix it." Hauser was quiet for a long moment, then reached for his phone. "Get me everyone we have who knows anything about prefabricated construction. I don't care if they're building chicken coops or grain silos. If they can design something that ships flat and goes up fast, I want them in Rhode Island by next week." He hung up and looked at Webb. "We're about to approve some radical solutions." March 16, 1942, 4:15 a.m., Quonset Point. Grosvenor's office smelled like stale coffee and desperation. 3 people who'd never met before today sat around a table covered in failed blueprints, and nobody was pretending this would be easy. Judith Reardon spread her own drawings across the table, pushing Grosvenor's calculations aside without apology. She was 34, one of maybe a dozen women in the country with a structural engineering degree, and she hadn't traveled 600 miles from Iowa to be polite about bad design. "You're thinking like an architect," she said, tapping Grosvenor's sketch of the modified Nissen hut. "That's your problem." Grosvenor felt his jaw tighten. "I'm thinking like someone who needs to shelter 50,000 men before summer." "No, you're thinking like someone trying to make buildings." Reardon pulled out a photograph of a massive curved structure. "This is a grain silo I designed outside Des Moines. Corrugated steel, self-supporting arch, no internal frame. It survived a tornado last spring that flattened every barn within 5 miles. Marcus Chen leaned forward, studying the photograph. The metallurgist from Pittsburgh looked like he hadn't slept in days either. His shirt wrinkled and coffee-stained. "Steel doesn't support itself. You need structural framing." "That's what everyone said." Reardon's smile had an edge to it. "Until they saw my barns still standing after the storms hit. The arch distributes the load. The corrugations add rigidity. You don't need wood or internal supports if you design the geometry correctly." Grosvenor wanted to argue, but he'd just spent 3 weeks proving conventional thinking didn't work. "The British design uses wooden frames specifically because—" "The British design weighs 3 tons and requires concrete foundations," Reardon interrupted. "How are you planning to pour concrete on a coral atoll while Japanese bombers make daily visits?" "You're not. Which means everything you're trying to adapt is already obsolete." The silence that followed felt heavy. Chen broke it first. "Even if the arch works structurally, Pacific salt air will corrode steel in 8 months, maybe less." He pulled out a thick folder of calculations. "I've been running the numbers since they pulled me off submarine hull analysis. Standard steel, even painted, won't survive. We need hot-dip galvanizing on every single panel, and that adds weight and cost." "How much cost?" Grosvenor asked. $112 per unit, minimum." Grosvenor did the math. For 5,000 units, that was over $500,000 just for corrosion protection. The Navy would have his head. "The alternative is replacing every hut within a year," Chen continued. "Your choice. Pay now or pay 10 times more later when they all rust through and collapse." Reardon was still studying her own drawings. "We eliminate the wooden frame. We save weight. Eliminate the floor system entirely. We save more. Ship the panels nested. We reduce cargo space. If Chen's right about galvanizing, and he probably is, we build it in once and never worry about it again." "You want to eliminate the floor?" Grosvenor stared at her. "Soldiers sleeping on dirt?" "Soldiers sleeping alive," Reardon shot back. "You can add floors later as a separate project. But the basic shelter needs to achieve weather protection immediately, with whatever surface exists: coral, sand, gravel, dirt. The structure sits on it and keeps rain off heads. That's the mission. Grosvenor looked at Chen, who shrugged. She's not wrong. Every component we add is another failure point, another thing to corrode or rot or break during shipping. Outside, dawn was starting to break over Narragansett Bay. Grosvenor thought about the telegram in his pocket. 57 days left. "All right," he said finally, "we do this your way. But we're not drawing plans for 3 weeks and then building. We prototype fast, test immediately, fail quickly, and fix it. No traditional architecture process." Reardon nodded. "Agreed. We sketch it this morning, fabricate it this afternoon, and test it tonight." Chen raised his coffee cup. 2 radical solutions. None of them smiled. They all knew radical was just another word for probably won't work. Day 2. March 17, 1942. The British Quonset Hut blueprints covered an entire wall of the warehouse, and the more Grosvenor's team studied them, the clearer their fundamental problem became. The design was brilliant for World War I. France. It was catastrophically wrong for 1942 Pacific combat. Chen stood at the wall, marking problems with red chalk. "Wait, 3 tons disassembled. That's 6,000 pounds of steel and wooden framing. You need a crane just to unload the pieces from transport vehicles." He drew a circle around the foundation specifications. Concrete anchor bolts, minimum 8 inches deep into poured foundation. Tell me how Marines are supposed to pour concrete foundations on Guadalcanal while under artillery fire. Reardon joined him, adding her own marks. The internal wooden frame. See these support ribs every 4 feet? In Scottish weather, fine. In Philippine humidity with termites, these become hollow shells in 1 season. The entire structure depends on wood that will literally be eaten away. She moved to the ventilation drawings. 2 small windows. Designed for climate where you want to keep heat in. In tropical conditions with 95-degree heat and 90% humidity, this becomes a steel coffin. Men will pass out from heat exhaustion inside their own shelter. Grosvenor had spent 3 weeks trying to modify these exact problems. Every fix created new issues. Strengthen the frame? Added weight? Remove the wood? Lost structural support? Add ventilation? Compromised weather protection? Reduce foundation requirements? Decreased stability. The geometry is perfect, though, Reardon admitted. The semicircular arch naturally deflects wind and sheds water. That's why it survived since 1916. We keep that. Everything else goes. Everything? Grosvenor asked. The wooden skeleton? The heavy steel gauge? The complex foundation system? The inadequate ventilation? All of it. Reardon pulled out a fresh sheet of paper. We're not modifying the Quonset Hut. We're stealing its one good idea and rebuilding from scratch. Chen looked skeptical. You can't make corrugated steel self-supporting at this scale. Physics doesn't work that way. Physics works exactly that way if you calculate the arch radius correctly and use the corrugations for structural rigidity. Reardon started sketching rapidly. My grain silos prove it. The curve creates a compression ring. Each panel shares load with its neighbors. The corrugations act like I-beams built into the skin. Your silos don't need to survive typhoons with 140-mile-per-hour winds. No, they survive Iowa tornadoes, which are worse. Reardon kept drawing. The principle scales. We calculate the proper radius, determine optimal panel thickness, and design the joints to transfer loads efficiently. Grosvenor watched her sketch taking shape. It looked nothing like the British blueprint. Thinner panels, no internal frame, a simpler bolt pattern, more aggressive ventilation openings along the ridge. It looked insane. It also looked like it might actually work. "How long to build a prototype?" he asked. Reardon checked her watch. "The metalworking shop opens in 2 hours. If they start fabricating panels this morning, we can have something assembled by tomorrow night." "Do it," Grosvenor said. "And if this fails, we've got 55 days to come up with something else." Nobody mentioned what happened if they ran out of time. They were all thinking it. The Japanese wouldn't wait for American engineers to figure out proper ventilation. Day 3, March 18, 1942, 2:30 p.m. The metalworking shop foreman looked at Reardon's drawings like she'd handed him instructions for building a spaceship. "You want me to fabricate panels with no internal support structure?" Frank Kowalski had been bending steel for 20 years, and nothing in his experience said this would work. "Ma'am, with respect, corrugated steel doesn't carry building loads. It's roofing material." "It's roofing material when it's flat," Reardon said. "When you curve it into an arch and corrugate it properly, it becomes a structural element." Kowalski shook his head. "Steel needs framing. Joists, rafters, support beams. That's basic construction." Grosvenor watched the argument from across the shop floor, knowing this was the critical moment. If they couldn't convince their own fabricators, they'd never convince the Navy. Chen stepped forward with his calculations. "The corrugations create rigidity through geometric shaping. Each ridge acts like a miniature I-beam. When you form these into an arch, the curve naturally wants to hold its shape through compression forces." "Naturally wants to?" Kowalski's tone made clear what he thought of that engineering language. Buildings don't work on what they want to do. They work on what holds them up. Reardon's voice went quiet, in a way that made everyone pay attention. In 1941, a Category 3 tornado hit 3 miles from my grain facility in Des Moines. Wind speeds measured at 165 miles per hour. Every conventional building within the path was destroyed. Barns with proper wooden framing were reduced to splinters. My corrugated steel silos, with no internal supports, stood completely intact. Not damaged. Intact. She pulled out photographs from her briefcase. The images showed devastation surrounding perfectly preserved curved steel structures. The geometry works because the arch converts lateral wind pressure into vertical compression forces that travel through the curve to the ground. The corrugations prevent the panels from buckling under that compression, and the panels bolted together create a continuous ring that resists deformation. Kowalski studied the photographs. "This is a grain silo. You're talking about a building people sleep in. I'm talking about the same structural principles at different scale." Reardon pointed to her specifications. "We calculate the arch radius to optimize the compression ring. We size the corrugations for the span length. We design bolt patterns that create load paths between panels. The math is sound." Grosvenor finally spoke up. "Frank, we've tried conventional thinking. 3 prototypes, 3 failures. We're out of time and out of options. What you're asking violates every structural principle I learned," Kowalski said. "Good," Reardon replied, "because every structural principle you learned was designed for permanent buildings in stable climates. We're designing for temporary structures in combat zones, where conventional construction is impossible. Different problem requires different solution." Kowalski looked at the 3 of them, then back at the photographs of tornado damage. "All right, but when this collapses during testing, I'm putting it in writing that I told you it wouldn't work." Reardon smiled for the first time since arriving. "When it works, you can put that in writing, too." The fabrication began within the hour. By midnight, they'd have their first frameless panels ready. Nobody slept. They all stayed to watch the metal take shape. wondering if they were witnessing innovation or disaster. Day 5 through Day 18. March 20th, April the 2nd, 1942. The argument about dimensions consumed 2 full weeks of their rapidly shrinking deadline, and nobody was backing down. Grosvenor wanted the huts large enough to house 48 men comfortably. More capacity per unit meant fewer units to manufacture and ship. Chen insisted on smaller structures because larger panels became too heavy for field assembly. Riordan kept running calculations that said both approaches missed the real constraint. "It's not about what we want," she said for the 10th time that week. "It's about what actually ships." She'd spent 3 days at the rail yard in Providence, measuring flatbed cars and talking to freight supervisors. The numbers were brutal and non-negotiable. Standard rail car width, 10 feet. We need clearance on both sides for loading. That gives us maximum 8-foot panel width before we trigger special permit requirements. 8 feet wide? Grosvenor protested. "That's barely enough interior space for bunk beds." "No, 8-foot radius." Riordan drew it on the chalkboard. "Semicircular arch with 8-foot radius gives us 16 feet of interior width, 7 feet of headroom at the sides. Plenty of space." Chen was already calculating. 16 feet wide. But how long? Each section needs to be light enough for 4 men to lift and position. 20 feet per section, Riordan said. 2 sections connected end to end gives us 48 feet total length. That's 720 square feet of floor space. 2 sections means a joint in the middle, Chen pointed out. Another potential failure point. Or it means flexibility, Riordan countered. Need smaller shelter? Use 1 section? Need larger? Connect 3 or 4. The modularity is a feature. But the arch radius calculation proved far more complex than Grosvenor expected. Too flat, and wind forces could peel the structure apart. Too steep, and they wasted interior headroom while making the end walls geometrically difficult. Riordan filled notebook after notebook with load calculations, wind pressure coefficients, and structural analysis. Chen ran parallel calculations on material stress and panel thickness requirements. They argued over half-inch differences in radius like lives depended on it, because lives did depend on it. On day 12, Grosvenor lost his patience. "We're burning time calculating decimals while soldiers are sleeping in mud. Pick a number and move forward." "Pick wrong, and the structure fails in the first typhoon," Riordan shot back. "You want speed? Fine. Let's ship 5,000 units that collapse and kill everyone inside. That fast enough for you?" The workshop went silent. Grosvenor realized everyone had stopped working to watch. "I'm sorry," he said quietly. "You're right. Get it right first. Then get it done fast." Riordan's expression softened slightly. 8-foot radius creates a perfect semicircle. The math is elegant and the structural properties are optimal for the span we need. But we need to verify it can handle the loading. By day 15, they had mock-up panels fabricated and were conducting stress tests. They hung weights from the curved sections, applied lateral pressure, and measured deflection under various loads. The results surprised everyone. The 8-foot radius semicircle was extraordinarily rigid. Even under loads simulating hurricane-force winds, the deflection stayed within acceptable limits. "It's the compression ring effect," Chen admitted, reviewing the data. "The curve really does distribute forces the way you predicted." Day 18 brought the final decision. 16 feet wide. 48 feet long in 2 24-foot sections. 8-foot radius arch. Panels sized for 4-man teams to handle. Total enclosed space, 720 square feet. Capacity, 36 men with bunks. Or conversion to offices, medical stations, supply storage. Now we build a complete prototype, Grosvenor said. They had 39 days left until the July deadline. 39 days to go from sketches to 5,000 manufactured units shipped across an ocean. Reardon looked exhausted, but determined. Then we better make it work on the first try. Nobody believed they'd get that lucky, but they were all committed to trying anyway. April 18, 1942, 6 a.m., Quonset Point. 6 sailors stood in the warehouse looking at 96 panels of corrugated steel stacked against the wall, a box of bolts, and a set of illustrated instructions that made the whole operation look deceptively simple. Petty Officer Second Class Raymond Torres picked up the instruction sheet. "Ma'am, with respect, this looks like we're assembling a giant tin can." "That's exactly what you're doing," Reardon said. "A tin can strong enough to survive a typhoon. You have 4 hours of instruction. Then you build it." Grosvenor watched from the observation platform as his team trained the assembly crew. Everything depended on this moment. All the calculations, all the arguments, all the sleepless nights came down to one question. Could exhausted men with basic tools actually put this together? The training went fast. How to identify panels by their numbered sequence, how to overlap the edges correctly, how to align bolt holes, how to use the level to ensure the arch stayed true. Torres and his crew asked good questions and caught potential problems that nobody had considered. "What happens if we cross-thread a bolt?" one sailor asked. Chen grimaced. "Don't. Every fastener matters. Cross-thread it, and you've created a weak point that could fail under stress." At 11 a.m., the training ended. The real test began. Torres divided his crew into pairs. 2 men on the end walls, 4 wrestling the curved panels into position. The warehouse filled with the sound of metal scraping against metal, wrenches clicking, and occasional cursing when panels didn't align perfectly. Grosvenor checked his watch every 15 minutes. Noon, 1 p.m., 2 p.m. The structure was taking shape, but slowly, painfully slowly. By 4 p.m., they'd completed half the assembly. The partial arch stood like a steel skeleton, and Grosvenor could finally see what the finished structure would look like. It was strange and utilitarian, and somehow more substantial than he'd expected. But they were nowhere near done. "They're exhausted," Chen observed, "and these are fresh sailors working in a controlled environment. Marines landing on hostile beaches will be operating on even less sleep and more stress." Reardon said nothing, but her expression showed she was thinking the same thing. 6 p.m. came and went. The crew took a quick meal break and came back to finish. The last panels went up under work lights as darkness fell outside. Finally, at 8:17 p.m., Torres stepped back from the completed structure. "It's done. 14 hours and 17 minutes from start to finish." Grosvenor walked through the completed hut, inspecting joints and checking alignment. The construction quality was good. The panels had gone together correctly. The structure looked solid and weatherproof, and it was completely unacceptable. 14 hours, he said to his team after the assembly crew had left. "Landing schedules don't give Marines 2 full days to build shelter. They'll be lucky to get 8 hours before they need to move on to defensive positions." "They'll get faster with practice," Reardon offered, but her voice lacked conviction. "Not fast enough." Grosvenor pulled out the timeline. "We've got 39 days to production. If assembly takes 14 hours, the entire concept fails. Commanders won't deploy structures that consume that much time and manpower." Chen leaned against one of the panels. "The bottleneck is the floor system. Did you watch? 6 hours just on laying and securing the wooden floor planks." Grosvenor had watched. The floor had been the slowest, most frustrating part of the entire assembly. planks that didn't quite fit, fasteners that required pre-drilling, leveling that demanded constant adjustment. The floor also adds the most weight, Chen continued. 1,200 pounds of lumber per unit. That's shipping space we're wasting on the component that's slowest to install and first to rot in tropical humidity. Reardon walked to the center of the hut and looked up at the curved steel ceiling. What if we just eliminated it entirely? The floor? Grosvenor stared at her. You want soldiers sleeping on bare ground? I want them sleeping alive. Reardon's voice was sharp. Every minute they spend assembling floors is a minute they're exposed and vulnerable. Every pound of floor planks is a pound we could be shipping as ammunition or medical supplies. And every piece of wood we put in contact with tropical ground is guaranteed to rot within months. You're talking about making men live in worse conditions. I'm talking about prioritizing survival over comfort. Reardon interrupted. The mission is weather protection. Keep rain off their heads. Keep wind from knocking down their shelter. The ground surface, whether it's coral or sand or dirt, provides the floor naturally. If specific applications need finished floors later, they can add them as separate projects. But the basic shelter achieves its primary function without them. Chen pulled out his calculator and started running numbers. Eliminate the floor system. We cut approximately 6 hours from assembly time. We reduce shipping weight by 1,200 pounds per unit. We remove the primary rot vector and the most labor-intensive component. Grosvenor looked at the completed prototype. They'd worked so hard to get here, and now Reardon wanted to tear out a fundamental element. But he couldn't argue with the math. 14 hours was too slow. The floor was the problem. All right, he said finally. We rebuild without the floor. But if this doesn't cut assembly time to 8 hours or less, we're out of options. Reardon nodded. Then we better make sure it works. They had 38 days left. April 19th, 1942, 3 a.m. Grosvenor couldn't sleep. The decision to eliminate the floor felt wrong in ways he couldn't fully articulate. He stood in the prototype hut, alone in the darkness, trying to see it through the eyes of a Marine who'd been fighting for 3 days straight. Would that Marine care about a finished wood floor? Or would he just want a dry place to collapse? The warehouse door opened. Reardon appeared, also unable to sleep apparently. Having second thoughts? She asked. Having all the thoughts. Grosvenor gestured at the floor beneath them. We're asking men to live like they're camping, in a war zone. We're asking men to assemble shelter in 1 day instead of 2, which might be the difference between surviving the first night or not. Reardon sat on one of the wooden floor planks they'd be removing. I know what you're thinking, that we're cutting corners, that we're prioritizing speed over dignity. Aren't we? No. We're prioritizing function over appearance. Reardon's voice carried an intensity he hadn't heard before. My father was at Belleau Wood in 1918. Spent 6 months in trenches filled with mud and water. He said the men who survived weren't the ones with the best equipment or the nicest quarters. They were the ones whose basic needs got met consistently. Dry, protected from elements, able to rest between operations. She stood up, pacing the length of the hut. This floor looks nice, feels substantial, makes the hut seem more like a real building. But it serves exactly one purpose, making us feel better about what we're asking men to accept. The floor doesn't keep them drier, doesn't make them safer, doesn't help them rest better. It just makes us feel like we gave them something proper. Grosvenor had to admit she had a point. The floor was psychological comfort for the designers, not practical benefit for the users. What about hygiene? He asked. Disease prevention? Sleeping on bare ground in tropical environments? They're already sleeping on bare ground in canvas tents that collapse during storms, Reardon countered. At least this gives them solid walls and a roof that won't leak. And for installations where finished floors matter, medical facilities or command posts, they can add them later as secondary construction. But the basic shelter achieves its mission without them. The next morning, Grosvenor called a full team meeting. Chen arrived with revised weight calculations. Reardon brought new assembly timeline projections. And Kowalski from the fabrication shop joined them, representing the perspective of men who'd actually be building these. From a manufacturing standpoint, removing the floor simplifies everything, Kowalski said. No lumber sourcing, no pre-cutting planks to size, no quality control on wood components. We focus exclusively on steel fabrication, which we're set up to handle at scale. Chen added his analysis. 200 pounds saved per unit. Multiply by 5,000 units. That's 3,000 tons of shipping capacity freed up. That's equivalent to 15 Liberty ships worth of cargo space. 15 ships we can use for ammunition, vehicles, medical supplies, or additional hut units. The math was becoming undeniable, but Grosvenor still felt the weight of making soldiers' lives harder. What about morale? He asked. The psychological impact of asking men to accept less. Reardon pulled out a letter. This arrived yesterday from a Lieutenant Cooper in the Philippines. Field report on current conditions. She read aloud. Men sleeping in tents that flood during rains. Waking with uniforms soaked. Equipment corroding. Pneumonia cases increasing. Request any shelter improvement possible. Immediate need greater than eventual comfort. She set the letter down. They're not asking for perfect. They're asking for better than what they have now. A steel structure that keeps rain out and stands up to wind is enormously better than canvas tents that collapse. We're not asking them to accept less. We're offering them more than they currently have. The room was quiet. Finally, Kowalski spoke up. My nephew is with the 1st Marines, just shipped out to the Pacific last month. If he writes home saying he's got a roof over his head that doesn't leak and walls that don't blow down, my sister won't care if there's a wooden floor. She'll care that her son is dry and has a place to rest. Grosvenor looked around the table. Chen nodded agreement. Reardon waited for his decision. All right, we eliminate the floor from the standard design. He made notes on the specification sheet. But we document the option to add floors as secondary construction for installations that require them. And we run another assembly test immediately to verify this actually cuts the time like we're projecting. When? Reardon asked. Grosvenor checked the calendar. Tomorrow. We disassemble the prototype, remove all floor components, and time a fresh assembly. If it doesn't get us to 8 hours or less, we're in serious trouble. They had 37 days until the July deadline. 37 days to get from modified prototype to 5,000 units manufactured and shipped. The decision was made. Now they had to prove it worked. Nobody slept that night either. They all knew the next test would determine whether this entire project succeeded or failed. April 21st, 1942, 7:45 a.m. The telegram sat on Grosvenor's desk like a bomb waiting to detonate. He'd read it 3 times already, and each reading made his stomach sink further. Panama test unit failure. Stop interior condensation. Severe. Stop water. Dripping from ceiling. Stop daytime temperatures 115 degrees. Stop structure. Uninhabitable. Stop. Recommend. Project. Termination. Stop. Termination. After 6 weeks of work, after solving the weight problem, and the assembly problem, and the structural problem, They were being told to quit. Chen arrived first, reading over Grosvenor's shoulder. His face went pale. "When did this come in?" 20 minutes ago. From the Canal Zone test facility. Grosvenor handed him the full report that had followed the telegram. They shipped a prototype down there 3 weeks ago to test tropical performance. The results are catastrophic. The report described conditions that sounded like a nightmare. When the hot, humid Panamanian air hit the relatively cooler steel panels at night, moisture condensed on every interior surface. By morning, water literally dripped from the ceiling like rain. Anything stored inside corroded overnight. Men couldn't sleep because they woke up soaked. During the day, temperatures inside the sealed steel structure climbed to 115 degrees. Soldiers who entered for more than 15 minutes showed signs of heat exhaustion. Equipment failed. The space was fundamentally uninhabitable. Reardon arrived and immediately sensed the mood. "What happened?" Grosvenor handed her the telegram without speaking. She read it, then read the detailed report. Her expression never changed, but Grosvenor saw her grip tighten on the papers. "The ventilation design is inadequate," she said finally. "We knew the 2 small windows from the British design wouldn't be enough. We should have addressed this earlier." "We did address it," Grosvenor said, hearing the exhaustion in his own voice. "We added louvers at both ends. Apparently, that's not sufficient." "It's not even close to sufficient." Chen had been running calculations while they talked. "We need aggressive air movement. The heat buildup during the day creates rising air that has nowhere to go. At night, that same sealed environment traps humid air that condenses when it touches cold steel. We've essentially built a terrarium." A knock on the door interrupted them. A Navy messenger entered with another telegram, this one from Washington. Admiral Whitmore's message was brief and devastating. "Review Panama report with extreme concern. Your design creates steel ovens that rain on sleeping men. This is unacceptable for deployment. Provide revised solution within 72 hours, or project will be cancelled. Lives depend on this working correctly." 72 hours. 3 days to solve a fundamental physics problem that had just destroyed their entire concept. Grosvenor felt something break inside him. The pressure of 6 weeks, the impossible deadline, the weight of knowing soldiers were suffering while he failed to deliver solutions, all of it crashed down at once. "We're done," he said quietly. "We can't solve physics. Hot air rises, cold surfaces condense moisture. Those are laws of nature, not engineering problems." "Everything is an engineering problem," Reardon said, but her voice lacked its usual certainty. "Then engineer a solution," Grosvenor snapped, "because I've got nothing. We've sacrificed the floor for assembly speed. We've eliminated the structural frame for weight savings. We've solved every logistical challenge thrown at us. And none of it matters because men can't survive inside what we've built." The office went silent. Chen stared at his calculations. Reardon looked at the Panama report again, as if reading it another time would change the results. "We need ventilation at the ridge line," she said finally. "Not just at the ends, along the entire length of the arch." Chen's head snapped up. "You want to cut holes in the compression ring? That's insane. Every opening is a structural weak point. You'll compromise the entire load-bearing capacity. Then we design openings that don't compromise it." Reardon grabbed a pencil and started sketching. Louvers positioned at calculated intervals, framed with reinforced edges that actually strengthen the surrounding panels, create negative air pressure that pulls hot air up and out. That's not how ventilation works in a sealed arch structure. That's exactly how it works if we design it correctly. Reardon's frustration finally showed. We've been treating ventilation as an afterthought. Two windows at the ends because that's what the British design had. But we're not in Scotland. We're building for tropical environments where heat management is as critical as structural integrity. Chen studied her sketch. Even if the ventilation solves the daytime heat, what about nighttime condensation? The steel will still be cooler than the ambient air. Physics doesn't change because we add more holes. But airflow changes, Reardon countered. Moving air prevents condensation from forming. We need continuous air movement, day and night. Ridge vents create natural convection. Hot air rises and escapes. Cooler air enters at ground level. Constant circulation. You're describing a chimney effect. Exactly. The arch shape naturally encourages vertical air movement. We're just giving it somewhere to go. Grosvenor wanted to believe her, but the Panama report was real data, not theoretical calculations. How much will this cost? How much time will it add to assembly? How do we even test this before the 72-hour deadline? Reardon did quick calculations. Additional louvers, reinforced framing for the openings, hardware to make them adjustable for different climate conditions. $47 per unit. Maybe more. The number hit Grosvenor like a punch. They were already over budget. Adding $50 per unit across 5,000 units meant $250,000 in additional costs. The Navy will never approve it, he said. The Navy will approve soldiers not dying from heat stroke, Reardon shot back. Cost is irrelevant if the structure doesn't work. Chen had been quiet, running his own calculations. The structural impact isn't as bad as I thought. If we frame the vents correctly and position them to avoid stress concentration points, we might actually be able to maintain integrity while improving airflow. Might, Grosvenor repeated. We're betting the entire project on might. We're betting it on physics and engineering, Reardon said, which is all we've ever had. The three of them looked at each other. Outside, dawn was breaking over Narragansett Bay. They had 71 hours left to redesign the ventilation system, fabricate new components, install them in the test unit, and somehow prove they worked. Start designing the vents, Grosvenor said finally. I'll call Washington and buy us more time. Chen, figure out the structural reinforcement requirements. We work through the night if we have to. Nobody moved at first. The weight of potential failure hung heavy in the office. Then Reardon stood up. We've solved every other impossible problem they've thrown at us. This is just one more. She didn't sound convinced, but she headed to the drafting table anyway, and the others followed. 29 days until the July deadline, and now 71 hours to save the project from cancellation. Day 31, April 22nd, 1942, 2:17 a.m. The warehouse lights had been on for 43 hours straight. Empty coffee cups covered every horizontal surface. 3 exhausted engineers stared at the same problem from different angles, and nobody was willing to back down. Reardon's ventilation design covered an entire wall. Ridge vents every 8 feet along the arch's peak. Large louvers at both end walls. Adjustable openings along the lower sides. It would move air aggressively and solve the condensation problem. It would also weaken the structure catastrophically, according to Chen's stress calculations. You're creating 14 penetrations in the compression ring, Chen said, his voice hoarse from hours of argument. Each one reduces load capacity. Stack them up, and you've got a structure that might handle normal weather, but will fail in the first typhoon. Your calculations assume the openings aren't reinforced, Reardon countered. I'm not just cutting holes. I'm framing each vent with structural elements that distribute the loads around the opening, which adds weight, complexity, and assembly time. Everything we've been trying to eliminate. Grosvenor had stopped participating in the argument around midnight. Now he just watched them circle the same points repeatedly, knowing they were all right and all wrong simultaneously. The ventilation was necessary, the structural integrity was necessary, cost and complexity mattered, assembly speed mattered, every requirement conflicted with every other requirement. "Stop," he said quietly. They kept arguing. "Stop!" louder this time. Chen and Reardon finally looked at him. "We're solving the wrong problem," Grosvenor continued. "We're trying to make perfect ventilation work with perfect structural integrity. But we don't need perfect. We need good enough to keep men alive." He walked to Reardon's drawings. "How many vents do we actually need to prevent lethal heat buildup? Not optimal comfort. Minimum survivability." Reardon considered. 6 ridge vents instead of 14. Larger end louvers to compensate. It reduces airflow efficiency by about 30%, but should still prevent dangerous temperatures. "Chen, can the structure handle 6 reinforced openings instead of 14? Chen ran through his notes. 6 strategic positions, properly framed, with load paths designed around them? Yes, it compromises the ideal compression ring, but maintains acceptable safety margins for the wind loads we're designing for." "What about the condensation?" Reardon asked. 6 vents might not move enough air at night to prevent moisture buildup." "Then we add one more element," Grosvenor said, the solution forming as he spoke. "Insulation blankets. Optional components that installations can add for extreme humidity environments. The blankets create a thermal barrier between the steel and interior air. Reduces condensation without requiring additional structural penetrations. Insulation adds cost," Chen pointed out. "Making it optional means installations that don't need it don't pay for it," Grosvenor countered. "Pacific Islands with extreme humidity get insulation kits. Drier climates skip them. The basic structure works everywhere, with climate-specific modifications available." Reardon was already sketching the compromise design. 6 ridge vents positioned at calculated intervals. Oversized end louvers for maximum airflow. Each opening framed with reinforced edges that transferred loads to adjacent panels. Chen checked the structural implications. Load capacity drops by 12% from the ideal no-penetration design, but remains 40% above minimum safety requirements. We've got margin for error. "What about assembly time?" Grosvenor asked. "The reinforced vents are prefabricated components," Reardon said. "They bolt in like any other panel. Adds maybe 30 minutes to total assembly. The end louvers replace the solid end wall panels, so no time increase there." "Cost?" Chen calculated quickly. $47 per unit for the ventilation components. Insulation kits another $30 for installations that need them. Total cost increase between $47 and $77 depending on climate requirements. Grosvenor did the math. For 5,000 units, they were looking at $235,000 to $385,000 in additional costs. The Navy would hate it. But the alternative was abandoning the entire project. "We build a test unit with the compromised design," he decided. "Install it in the existing Panama prototype and monitor performance for 48 hours. If it solves the temperature and condensation problems without structural failure, we have our solution." 48 hours isn't enough data, Chen protested. "It's what we've got. The deadline isn't moving, and Washington isn't interested in long-term studies. They want proof it works, or they cancel the project." Reardon looked at her sketch. "This could work. It's not elegant, but it's functional." "Functional is all we need," Grosvenor said. "Elegant doesn't keep soldiers alive." They called the Panama facility at $3 a.m. and arranged for the modified components to be fabricated and shipped south on the fastest available transport. Installation would happen within 24 hours. Results would follow within 48. Either the compromised design would work, or the entire Quonset Hut project would die. Chen finally spoke what they were all thinking. We've eliminated the floor, weakened the structure with vent holes, and added costs we can't really afford. We've compromised every aspect of the original design. No, Reardon said quietly. We've adapted to reality. That's what engineering actually is. Outside, the first light of dawn appeared over the bay. Day 31 becoming day 32. 28 days until the July deadline. They'd either solved the condensation crisis or destroyed their last chance at success. The answer was already on its way to Panama. Now they just had to wait. June 10th, 1942, 9:30 a.m. Quonset Point. The complete hut stood in the warehouse like a monument to exhausted determination. 96 corrugated steel panels bolted together to create 720 square feet of enclosed space. Total materials cost $1,394. Total weight 9,000 pounds exactly. Grosvenor walked through it for the 100th time, checking joints, testing bolt tension, looking for any flaw that would doom them during final inspection. The Panama modifications had worked. Temperature tests showed the interior stayed within survivable ranges, even during peak heat. Condensation had dropped to manageable levels. They'd done it. Against every obstacle, every setback, every moment of doubt, they'd created a structure that actually worked. The celebration lasted approximately 4 minutes. That's when Lieutenant Commander Raymond Kellerman walked through the warehouse door carrying a leather briefcase and the kind of expression that meant bad news. "Commander Kellerman," Grosvenor said, trying to keep his voice neutral, "we weren't expecting Navy inspection until next week." "This isn't an inspection." Kellerman set his briefcase on a workbench and pulled out folders thick with data. "I'm here from Pearl Harbor with updated environmental specifications for Pacific deployment." Chen and Reardon joined them, sensing the shift in mood. Kellerman spread meteorological charts across the bench. Typhoon Gloria hit Guam in November 1940. These are the recorded measurements. His finger traced across data columns. Sustained winds of 140 miles per hour. Gusts reaching 180. Storm surge 20 feet. Rainfall 15 inches in 6 hours. Grosvenor felt his chest tighten. "Our design specifications call for structures capable of surviving 100-mile-per-hour winds." "I know what your specifications call for." Kellerman's tone wasn't unkind, but it was absolute. "I'm telling you, they're inadequate. The Pacific doesn't care what you designed for. It's going to throw everything at these structures. And if they fail, the result isn't property damage. It's dead servicemen." He pulled out more reports. The 1935 Labor Day hurricane in the Florida Keys produced winds so powerful they drove wooden planks through palm trees like spears. Sand blasted paint off concrete buildings. If your huts fail in conditions like that, we're not just losing shelter. We're creating shrapnel that kills everyone nearby. The warehouse was silent, except for the sound of wind outside, suddenly seeming ominous. "You're telling us we're 40% short on wind resistance," Reardon said flatly, "after 2.5 months of development. I'm telling you the Pacific is more hostile than your calculations assumed." Kellerman looked at each of them. "I've seen what typhoons do to structures. I've walked through bases where buildings that looked solid were reduced to twisted metal. The men who designed those buildings thought they were adequate too." Chen was already pulling out his structural calculations, flipping through pages with increasing desperation. Our compression ring design, the arch geometry, the corrugation reinforcement, all of it was calculated for 100-mile-per-hour sustained winds with gusts to 120. We can't just recalculate for 40% higher forces. The physics doesn't scale linearly. Then you need to test it, Kellerman said. Not calculate, test. Put sensors on a full-scale prototype and expose it to real weather conditions that simulate what you'll face in the Pacific. We don't have access to 140-mile-per-hour winds in Rhode Island, Grosvenor said, hearing the defeat in his own voice. No. But you get nor'easters, and you've got winter storms that can hit 75 to 80 miles per hour with heavy snow loading. Kellerman pointed to the weather data. Build an instrumented prototype. Wait for the next major storm. Measure what actually happens under real stress instead of theoretical calculations. And if it fails, Reardon asked, then you redesign before you kill people. The simple brutality of that statement hung in the air. 3 months of work. 3 months of problem-solving and compromise and exhaustion. And now they were being told it might not be enough. Grosvenor looked at his team. Chen's face had gone pale. Reardon stared at the typhoon data like it was a personal insult. How long do we have? Grosvenor asked. The July deadline hasn't changed, Kellerman said. But I'm not approving deployment of structures that haven't been stress-tested under realistic conditions. You want my signature? Prove this design survives real weather. He packed up his briefcase and headed for the door, then paused. For what it's worth, I hope you're right. We desperately need this to work. But hope doesn't keep men alive in typhoons. Engineering does. After he left, the three of them stood looking at the prototype that had suddenly become inadequate. We need a storm, Chen said finally. A big one. And we need it soon. Grosvenor checked the calendar. June 10th. 3 weeks until the July deadline. Then we pray for bad weather, he said. And we build the most instrumented test structure in naval history. They had bet everything on their calculations being correct. Now they had to prove it with real wind, real rain, and real stakes. 20 days left to wait for a storm that might not come or might prove them completely wrong. June 14, 1942, 11:45 p.m. Davisville, Rhode Island. The anemometer readings were climbing. 52 miles per hour. 58. 63. The nor'easter that had been forecast as a minor spring storm was intensifying into something far more serious. Grosvenor stood in the observation shelter 200 yards from the instrumented prototype, watching data stream in from the 20 sensors they'd installed across every critical stress point. Strain gauges on the bolt connections, pressure sensors on the panels, deflection meters at the arch crown, everything feeding into recording equipment that would either prove their design or destroy it. Chen hunched over the instruments, calling out readings every 30 seconds. Wind speed 67 miles per hour, gusts to 74. Crown deflection 0.8 inches. Panel stress within normal parameters. Snow accumulation? Reardon asked from her position at the weather station. 4 inches and climbing. The loading is increasing faster than forecast. This wasn't the 140-mile-per-hour typhoon they needed to simulate, but it was the best nature could offer in Rhode Island in June. A powerful nor'easter with high winds, heavy snow loading, and enough force to stress-test the fundamental design principles. If the structure failed here at 75 miles per hour, it had no chance against Pacific typhoons. If it survived, they'd at least have proof that the basic engineering was sound. The wind howled around their observation shelter. Through the darkness and blowing snow, Grosvenor could barely see the prototype's silhouette. Just a curved shadow against the storm, looking small and fragile against nature's violence. "Gust to 82, Chen called out. "Crown deflection 1.1 inches, still elastic deformation, returning to baseline between gusts." "Panel joints?" Reardon demanded. Holding. No separation. No indication of fastener failure. The storm intensified. Midnight passed. On 1 a.m., the wind maintained speeds in the 70s with gusts breaking 80. Snow piled against the curved structure, creating exactly the kind of asymmetric loading that could collapse a poorly designed arch. Grosvenor watched the numbers, trying to interpret what they meant. The deflection was larger than their calculations had predicted, but the structure was returning to its original shape after each gust. That meant elastic behavior, not plastic deformation. The materials were stressed, but not permanently damaged. At 1:47 a.m., a massive gust hit. The anemometer peaked at 87 miles per hour. Crown deflection 2.3 inches. Chen's voice rose with alarm. That's beyond our predicted range. Everyone held their breath. 2.3 inches of deflection meant the arch was flexing significantly. Too much flex, and the compression ring could fail. Panels could separate. The entire structure could collapse. The sensors showed the deflection holding at maximum for 3 seconds. 4, 5. Then the wind eased slightly and the numbers began dropping. 2 inches. 1.8. 1.5. Back to baseline. It returned to original shape, Chen said, disbelief in his voice. No permanent deformation. The structure absorbed the stress and recovered. Reardon was checking the panel joint data. All fasteners maintained integrity. No bolt slippage. No panel separation. The compression ring distributed the load exactly as designed. The storm continued through the night, but the critical test had passed. The prototype flexed with each major gust, then returned to true. The corrugated steel panels acted like springs, absorbing energy and releasing it without permanent damage. The arch geometry converted lateral wind forces into vertical compression that traveled through the structure to the ground. By 4:30 a.m., the storm was weakening. By 6 a.m., dawn revealed the test results in full. The prototype stood intact. Snow had drifted around the base, but slid off the curved surface as designed. No panels had separated, no fasteners had failed. The structure looked exactly as it had before the storm, except for a light coating of ice. Grosvenor, Chen, and Reardon approached the hut slowly, almost afraid to believe what they were seeing. They'd watched the sensor data all night, but seeing the physical reality was different. Chen ran his hands along the panel joints, checking for any gap or movement. It's solid. Everything held. Reardon inspected the ventilation louvers. No damage, no deformation. The reinforced openings performed as designed. Grosvenor walked inside. The interior was dry. No leaks, no condensation despite the temperature differential. The space felt protected, secure, exactly what a soldier would need after days of combat. "It works," he said quietly. "The math actually works." They stood in the hut as morning light filtered through the end louvers. Exhausted and overwhelmed and profoundly relieved. The structure had survived 87-mile-per-hour winds and heavy snow loading. Not the full 140 miles per hour of a Pacific typhoon, but enough to prove the fundamental engineering was sound. The compression ring concept worked. The corrugated panels provided the rigidity they'd calculated. The arch geometry distributed loads as predicted. "It's not just strong," Reardon said, echoing her earlier assessment. "It's elegant." Chen was already calculating extrapolations. "If we can handle 87 miles per hour with deflection that returns to baseline, the scaling suggests we'd survive significantly higher forces with acceptable deformation." "Will Kellerman accept this as proof?" Reardon asked. Grosvenor pulled out the data recordings. Pages of sensor readings showing structural behavior under real-world stress. He asked for testing under realistic conditions. We gave him better than that. We gave him measurements. They had 16 days until the July deadline. 16 days to get final approval, begin manufacturing, and start shipping to the Pacific. But for the first time in 3 months, Grosvenor allowed himself to believe they might actually succeed. The prototype had survived the storm. Now they just had to build 5,000 more. June 16, 1942, Washington, D.C. The War Production Board conference room held 14 men who controlled America's industrial capacity. Grosvenor stood at the head of the table with his storm test data, knowing the next 20 minutes would determine whether 3 months of work meant anything. Admiral Whitmore made the introductions brief. Gentlemen, we've been reviewing the Quonset Point Shelter Project for Pacific deployment. Commander Grosvenor has test results. I suggest we listen before making judgments. Grosvenor laid out the photographs first, the prototype before the storm, standing clean and new. The prototype after, buried in snow, but structurally intact. Then came the sensor data, page after page of measurements showing exactly how the structure behaved under stress. 87-mile-per-hour winds, he said. Heavy snow loading. The structure deflected a maximum of 2.3 inches at the crown, then returned to original shape with no permanent deformation. Every fastener held. Every panel joint maintained integrity. A board member named Hutchins interrupted. You're asking us to approve mass production based on one storm test? That's not how engineering validation works. It's how validation works when we're out of time, Grosvenor replied. The alternative is shipping soldiers to the Pacific with no shelter improvement while we conduct 6 months of additional testing. The alternative is not shipping defective structures that collapse and kill people, Hutchins shot back. The room erupted in argument. Some board members supported immediate production. Others demanded more testing. The debate consumed 15 minutes with no resolution. Finally, Whitmore stood up. The room went silent. Gentlemen, I've read Lieutenant Commander Kellerman's assessment from Pearl Harbor. He witnessed the storm test remotely through data transmission. His conclusion states, and I quote, "The Quonset design demonstrates sound engineering principles and acceptable performance under stress conditions. Recommend approval for limited production with field testing to follow. Limited production means we manufacture while we validate, not validate while men sleep in mud." He looked at Grosvenor. How fast can you scale production? 10 steel fabricators are ready to retool immediately. We've identified facilities in Pennsylvania, Illinois, Ohio, and Michigan. With War Production Board priority, they can begin manufacturing within 2 weeks. Monthly output? Initial target is 1,500 units per week by August, scaling to 8,000 units monthly by December if field results support expansion. Hutchins wasn't finished fighting. The cost per unit? $1,394 for materials. Assembly requires approximately 8 hours with 6-man crews using basic tools. Compare that to conventional construction. Grosvenor had the numbers ready. Wooden barracks cost $12,000 in materials, require 400 man-hours of skilled carpentry, and take 6 weeks to build. The Quonset delivers shelter at 1/10 the cost in 1/20 the time. The room went quiet as the board members absorbed that comparison. What about the tropical performance issues? Another member asked. I saw the Panama reports. Solved through ventilation modifications, Grosvenor replied. Ridge vents and end louvers maintain acceptable interior temperatures. Optional insulation kits address condensation in extreme humidity environments. All modifications tested and validated. Whitmore called for a vote. All in favor of approving Quonset Hut production with initial order of 5,000 units for Pacific deployment. 9 hands went up, 4 opposed, 1 abstention. Approved, Whitmore declared. Production begins immediately. Priority shipping to West Coast ports for Pacific transport. Field commanders will receive first units by mid-August, with full deployment by October. The meeting adjourned. Grosvenor stood alone in the conference room for a moment, letting the reality sink in. They'd done it. Against every obstacle, every setback, every moment when failure seemed certain, they'd convinced the War Production Board to bet on their design. Now came the hard part, actually delivering 5,000 units in less than 8 weeks. He caught a train back to Rhode Island that evening. By the time he arrived at Quonset Point at midnight, Chen and Reardon were already working with Kowalski to finalize manufacturing specifications. "We're approved for production," Grosvenor announced. Reardon looked up from her drawings. "Then we better make sure these can actually be manufactured at scale, because designing one prototype is different from fabricating thousands." She was right. Every decision they'd made for the prototype, every compromise and modification, now had to translate into assembly line production across multiple facilities. Tolerances had to be precise. Quality control had to be rigorous. Supply chains had to deliver millions of pounds of steel on schedule. By July 1st, the first manufacturing facilities had retooled their production lines. The Strand Steel Corporation in Pennsylvania, Great Lakes Steel in Ohio, Fuller Construction in Illinois. 10 factories total, all converting from peacetime manufacturing to military shelter production. The first panels rolled off the line on July 8th. By July 15th, complete hut kits were being loaded onto rail cars heading west. Grosvenor watched the first shipment depart from the Providence rail yard. 40 flatbed cars, each carrying a complete Quonset hut. 40 structures that would cross the country by train, transfer to ships in San Francisco, and arrive in the Pacific within 6 weeks. Reardon stood beside him as the train pulled away. "Think they'll work?" "The math says they will." The math said a lot of things. Reality has a way of disagreeing. Grosvenor couldn't argue with that. But the train was already gone, carrying their design toward its ultimate test. Real soldiers, in real combat conditions, facing real Pacific storms. All they could do now was wait for the field reports and hope their engineering held up when it mattered most. 14 days until the original July deadline. They'd met it with 2 weeks to spare. Now the huts just had to survive actual war. August 7th, 1942. Guadalcanal, Solomon Islands. The first Quonset huts hit the beach 3 hours after the initial Marine landing. 6 complete kits unloaded from transport ships onto a shoreline still smoking from naval bombardment. The temperature was 94 degrees with humidity so thick it felt like breathing water. Corporal James Vickery watched the steel panels being unloaded and thought they looked insane. Curved metal sheets that were supposed to become buildings, while Japanese artillery still hammered positions 3 miles inland. The whole operation felt like someone's desperate joke. But orders were orders. His construction detail, 8 Marines who'd been fighting for 36 hours straight, were told to assemble shelter for the maintenance crews working on Henderson Field. The battered F-4F Wildcat fighters operating from the airstrip needed mechanics, and those mechanics needed somewhere that wasn't a hole in the ground. Vickery opened the instruction sheet, illustrated diagrams that made it look simple. Reality disagreed immediately. The panels were heavy, awkward, and kept sliding in the volcanic sand. The bolt holes didn't always line up perfectly. Every fastener required careful alignment, while sweat poured into their eyes and made the wrenches slippery. Around them, the war continued. Artillery crumped in the distance. Aircraft engines roared from the airstrip. Other Marines dug foxholes and strung communications wire and did all the 1,000 urgent tasks that combat required. Vickery's crew worked through the afternoon heat, wrestling with panels that seemed designed to catch every gust of wind and try to sail away. By 1900 hours, they had the first structure taking shape. The curved arch looked strange against the tropical vegetation, like something from another planet. By 2300 hours, they'd completed the assembly. 12 hours of work, slower than the specifications promised, but acceptable given the circumstances. The structure stood in a coconut grove that still showed scorch marks from the previous week's shelling. The maintenance crews moved in immediately, grateful for any space that provided shade and kept rain off their tools. The hut's interior was stifling hot, but the ridge vents and end louvers created enough airflow to make it survivable. 3 days later, August 10th, the structure faced its real test. Japanese bombers made their daily visit to Henderson Field at 14:30 hours. 18 twin-engine Bettys escorted by 0 fighters. The Marine anti-aircraft crews opened up, filling the sky with tracers and exploding shells. One bomber, damaged by AA fire, jettisoned its payload early. A 500-pound bomb fell short of the intended target, the airstrip, and detonated approximately 40 yards from Vickery's Quonset Hut. The explosion was catastrophic. Palm trees within 50 feet of the impact were simply gone, reduced to splintered trunks. Canvas tents in the area disintegrated into shredded fabric. The shockwave knocked Marines off their feet 200 yards away. Inside the Quonset Hut, 6 aviation mechanics were working on an aircraft magneto when the bomb hit. The blast wave slammed into the curved steel structure like a giant's fist. The entire hut rang like a bell, deafeningly loud in the enclosed space. Dirt, coral fragments, and shrapnel rattled against the exterior like deadly hail. The lights went out. Tool cabinets tipped over. Everything not secured went flying. For 5 seconds, the men inside thought they were dead. Then the ringing in their ears subsided enough to hear someone screaming for a medical check. Flashlights came on. The smoke cleared. They were alive, all 6 of them. Shaken, deafened temporarily, but alive. The hut had held. When they emerged, the devastation around them was total. Trees flattened, equipment scattered. A crater 15 feet deep where the bomb had detonated. And, standing in the middle of it all, the Quonset Hut, with its steel skin dented and scarred, but structurally intact. The curved surface had deflected the blast upward and around, rather than absorbing it directly. The corrugated panels had flexed with the shock wave, then returned to shape. The compression ring had distributed forces that would have collapsed a rectangular structure. Vickery stood looking at the structure, trying to process what he was seeing. The engineers who designed this had somehow predicted forces that shouldn't be predictable. They'd built something that survived conditions that killed everything around it. The field report reached Quonset Point 3 weeks later via military dispatch. Grosvenor read it twice, then handed it to Reardon without speaking. She read it and smiled. The first genuine smile he'd seen from her in 4 months. The math works. Chen looked over her shoulder at the report. It actually works. They'd designed it in a Rhode Island warehouse, tested it in a nor'easter, manufactured it across 10 factories, and now it had survived combat in the Pacific. The Quonset Hut wasn't theory anymore. It was proven. By September, production was ramping to 2,000 units weekly. By October, Quonset Huts were appearing on islands across the Pacific. The design that had seemed impossible in March was becoming the standard shelter for American forces throughout the theater. Grosvenor received letters from field commanders. Most were brief, pragmatic assessments of performance, but one stood out. From a Colonel Harrison at Espiritu Santo. Your huts survived a typhoon that destroyed every other structure on this base. Whatever you did in Rhode Island, it worked. Keep building them. They did. By war's end, over 170,000 Quonset huts would be deployed worldwide. But that August day on Guadalcanal, when the first hut survived its baptism by fire, that's when Grosvenor finally believed they'd actually succeeded. September 1942. Quonset Point, Rhode Island. Walter Grosvenor stood in the now empty warehouse where it had all started 6 months earlier. The prototypes were gone, shipped to testing facilities or salvaged for parts. The frantic energy had moved to manufacturing plants across the country. What remained was just a quiet space and the memory of impossible deadlines. The telegram sat on his desk. Not the one from March demanding radical solutions, but a new one from Guadalcanal. Simple, direct, devastating in its brevity. Huts survived direct near-miss stop all personnel. Safe stop request. Additional units immediately stop. Chen found him there an hour later. You should be celebrating. We did it. Did we? Grosvenor gestured at the empty warehouse. We solved one problem, built one thing. The war's going to last years. How many more impossible problems are coming? Probably hundreds, Chen admitted. But we proved something here, that you can solve physics problems under impossible pressure, that radical solutions actually work when you engineer them correctly. Reardon joined them, carrying a folder thick with field reports. You need to see these. Performance data from 17 different installations. The huts are exceeding specifications in almost every category. She spread the reports across the workbench. Typhoon survival at Tacloban, heat management in New Guinea, rapid assembly under fire at Tarawa. Each report documented conditions that should have broken the design and didn't. Super Typhoon Cobra hit the Philippines last week, Reardon continued. 140-mile-per-hour winds, exactly what Kellerman warned us about. Destroyed 80% of conventional structures on the base. Of 43 Quonset huts, 39 survived intact, 4 repairable, 0 total losses. The number hit Grosvenor harder than he expected. They'd designed for those conditions in theory, tested at lower intensities, extrapolated from calculations. But theory and reality were different things. Knowing that real soldiers survived a real typhoon because of engineering decisions made in this warehouse felt overwhelming. The Navy's requesting production increased to 10,000 units monthly, Chen said. They want them for every theater. Europe, North Africa, Alaska. Everyone sees what works in the Pacific and wants the same thing. Grosvenor looked at the reports, the data, the proof that their desperate gamble had succeeded. But his mind was already somewhere else. What happens after the war? He asked. We're building 170,000 of these things. That's not temporary. That's infrastructure. Reardon had clearly been thinking the same thing. Housing shortage is going to be massive when soldiers come home. These could solve that. Cheap shelter that goes up fast. Not pretty, but functional. Churches needing space. Schools facing enrollment explosions. Small businesses looking for affordable buildings. Chen was calculating possibilities. We didn't just build military shelters. We built a manufacturing system for rapid deployment architecture. The three of them stood in the empty warehouse, understanding that what they'd created would outlive the war that demanded it. Grosvenor thought about the March telegram, the impossible deadline, the 60 days to solve everything. They'd been trying to shelter soldiers in combat. Instead, they'd accidentally revolutionized prefabricated construction. You know what's strange? Reardon said quietly. In 50 years, People might be using these principles for things we can't even think about yet. Disaster relief, space stations, Mars colonies. The physics doesn't care what year it is. She was right. The compression ring, the self-supporting arch, the corrugated structural skin, all of it was based on mathematics that wouldn't change. Future engineers facing different impossible problems would rediscover the same solutions because the underlying physics remained constant. Grosvenor picked up the Guadalcanal telegram one more time. All personnel safe. That's what mattered. Not the legacy, not the future applications, not the engineering triumph. 6 mechanics survived a bomb blast because the math worked. Chen raised an imaginary coffee cup. To radical solutions, Reardon smiled. To solving impossible problems in 60 days. Grosvenor looked at his team, exhausted and accomplished, and already thinking about whatever came next. To keeping people alive, he said simply. Outside, another rail car loaded with Quonset huts departed for the West Coast. The design they'd created in desperation was becoming standard equipment. The temporary solution was proving permanent, and somewhere in the Pacific, soldiers were sleeping dry under curved steel roofs, never knowing about the arguments at 2 a.m., the failed prototypes, the condensation crisis, or the storm test that almost didn't happen. They just knew it worked. That was enough.